So, if you so here we last time we had that comparison of sodium, cesium and helium line. Okay. So, now you have a nice idea of what broadening is about and what is natural broadening. But then natural broadening is not the only broadening that is possible. So, there are some two different types of broadening. So, the line broadening mechanism can be divided into homogeneous broadening and inhomogeneous broadening. So, what do I mean by homogeneous broadening? By homogeneous broadening, if you consider a vessel of molecules, okay, or particles, and each particle has almost a similar interaction with the other. So, each particle is interacting with the other particle in a similar fashion. Okay. Even in a crystal, in a crystalline, each atom is interacting with its neighbors it's in a similar way. So, if I consider particle 1, its interaction with its neighbors is the same as particle 2, is the same as particle 3, is the same as particle 4. So, it's a homogeneous way of interacting with your neighborhood. Okay. So, that is why it is called, and whenever you are interacting with your neighborhood, you are giving rise to broadening. Okay. So, that is why it is called homogeneous broadening. For all the particles, it is equal. In case of inhomogeneous broadening, each particle within a collection of particles is interacting in a slightly different way from the other. It is in the same collection, but particle 1 may have a slightly different environment as compared to particle 2. Particle 3 may have a slightly more different environment as compared to particle 1 or 2. Okay. This can happen quite often in crystalline media also. So, if the crystal is made up of not the same elements, there are some other elements also embedded in it. So, each element will have a different environment. Okay. And in a gas also it can happen. Each particle is experiencing something different from its neighbors. Okay. So, now you have these are the broad partitioning of the broadening mechanism, homogeneous and inhomogeneous. Under homogeneous broadening, you have natural broadening, which I have described. But there is one more which is called collisional broadening, and collisional broadening is very important in a gas. Okay. And you will find, as I go through the derivation, you will see collisional broadening is much more than natural broadening. Quite often you can forget natural broadening and just concentrate on the collisional broadening only. And under inhomogeneous broadening, you have something called the Doppler broadening. So, I will be covering collisional broadening and Doppler broadening. Okay. Let us see how they work out. See, why do you get collisional broadening? Why does the line shape function broaden? What kind of line shape function do I get when there are collisions? Okay. So, here what I have shown is, okay, that particle is radiating in a sinusoidal kind of a function. Okay. Then it goes and collides with another particle. Okay. Here this is just representation of collision. When it collides, okay, it remains as a sine wave, but then its phase has changed. If you see, this had started off at this point, okay, but now after the collision, it's starting off, the wave is starting off here, wave of the radiation. Okay. Again it undergoes another collision and it starts radiating at this point, okay, and it remains as a sinusoidal. For the moment, just believe that it remains as a sinusoidal, nothing much has changed, and the frequency remains as it is. It collides, the frequency remains, but the phase changes. That is what we have to understand. What impact does this phase change have on the broadening of the line? Okay. So, collisions are all random, time between successive collision obeys the Poisson's distribution. You have to recollect some of your statistical mechanics that you have studied. You have to remember Poisson's distribution, because if you recollect, Poisson's distribution is a derivative of binomial distribution, which is which describes the probability of random events. Okay. So, things are happening at random. So, you have a probability that n particles, say n particles, small n particles, maybe I can write it here, small n particles. And what is the probability that small n occurrences will occur in capital N number of ways? This will be given by a binomial function. Okay, you can just look through it, and Poisson's distribution is really a derivative of binomial. So, that is why we apply it here, because these collisions are happening randomly. So, so in the interval, so we are bothered about the random time. You know, there may be a mean time in which these collisions are happening. There is a mean time which is given by tau 0 here. Tau 0 is the mean time between collision. But then we want to know what is the probability in the interval psi and psi plus d psi. What is the probability that this collision, the probability of this time psi and psi plus d psi. Tau 0 is the mean time between collision, mean time is fixed. But then a time of psi and psi plus d psi, what is the probability that it will happen? So, here you have this time between these two collisions is this much. Visually you can see this is larger, this is smaller, but okay, there is a mean time. So, p psi d psi is 1 upon tau 0 e to the power minus psi upon tau 0 d psi. So, this, as you can see, it gives you a distribution of the possible times. Okay. And now, okay, so keep this in mind. So, you are going to use this Poisson's distribution, can't get rid of it. The emission wave, that means the electric field between the instants t0 and t0 plus psi, that is given by Et, emission wave, E0 e to the power I omega 0 t plus phi. Okay, I have introduced this phi here, because as I have said in this picture, your phase is changing. After each collision, the phase is changing. Now, that phase change has a lot of effect on the line shape function. So, I can't keep it as e to the power I omega 0 t, because that is not what is happening. Each time the phase is also changing. So, I bring in this factor phi, some people call it psi, and this is happening between the time t0 and t0 plus psi. So, at this time, suppose this is t0 at this dashed line and this is t0 plus psi. Okay. That is the electric field between this and this. Okay. So, this is also a big assumption actually, that electric field may have changed even frequency. That means omega 0 could have been something else which is different from the frequency here. But let us derive it, let us assume that the frequency, the central frequency does not change, omega 0 does not change after a collision, only the phase is changing. Okay. So, T0 between T0 and T0 plus psi. Now, I have to take the Fourier transform of this in order to get the spectrum, okay, as before. So, Fourier transform, the spectral composition is f omega, you take the integral E t e to the power I omega t dt. That is a formula for the Fourier transform. You integrate it over all the time. Now, all the time here is T0 and T0 plus psi, as I have said here. We are only bothered about this end of the time. Okay. E0 is a constant, and what you get is e to the power I omega 0 t minus omega t plus phi. It is just a bit of algebra. If you put this equation here, you will get this. Then you take the Fourier transform, that means you take this integral and this is what you get. Okay. This is your f omega. Okay. Here I have imaginary function, there is a I here, there is a I here, there is a I here. We want to be in the real world, so we have to get rid of the i's somehow. Okay. So, as we know, as we had done before, we had taken mod of f omega whole square, or you can say f omega star f omega. Okay, here that is the same as mod. Okay. So, the line shape function I will call it as w omega. In case of natural broadening, I had called it as g omega. So, this is w omega and it is proportional to f omega f star omega. So, I will do all that algebra there, I will do f omega f star omega, oh sorry, and this is the formula that you come across. For total spectral composition, include the Poisson's distribution too. Okay. So, this is a spectral composition of that sinusoidal wave which is undergoing collision and changing phase. Okay. This is a spectral composition. But do not forget that these collisions are happening randomly and there is a probability given by the Poisson's distribution. So, we include the Poisson's distribution along with this. So, we multiply this with this Poisson's distribution. So, I have 1 upon tau 0 integral of 0 to infinity, this factor, this whole factor is placed here and then this is the Poisson's plus. Okay. Now, I integrate out all the size 0 to infinity, I just integrate out all the size and I will be left with just the omegas and that is what I want, w omega. And that works out to be, you have to do all the transformations. I mean the algebra, you just do all that algebra and you will come to this function. Just have a look at this function, does not it look familiar? It looks like a Lorentzian function once again. Okay. If you compare with the previous slide, just looks similar to the Lorentzian function. Anything that has a x square plus a square in it, it is a Lorentzian function. Okay. 1 upon x square plus a square, okay, some term like this. See the similarity between this and this, and even in the previous slides you will know. So, this is so your line shape function for collisional line shape function is also a Lorentzian, just like in the natural line shape function. Okay. Now, the Lorentzian shape, the line width will be 2 upon tau 0 is equal to delta omega. So, you can compare these two and compare the previous slide Lorentzian functions and you will come to this conclusion. The full width at half maximum turns out to be 2 upon tau 0. Okay. So, delta omega, that is the full width half maximum and that is what we are looking for. Now, the time between collisions will depend on the mean free path, agree with that. It will depend on the speed at which those atoms or molecules are moving. It will depend on the pressure of the total gas. It will depend on the temperature of that gas and it will depend on the mass of those particles. Okay. All these things will affect the mean time between collisions. So, all these will affect your tau 0, which is the mean time between collisions, and obviously that will affect your full width half maximum delta omega. Okay. As an example, collision time of tau 0 is equal to 10 to the power minus 6 seconds or microseconds, 1 microsecond. So, what will omega be? What will delta omega be? will be 1 upon pi tau 0. Just put in all those formula here, do that little bit of algebra and you will get this. So, delta nu turns out to be 0.318 megahertz. We had seen before in the previous slides that megahertz gives the is the unit of delta nu or the full width half maximum. That is a measure of broadening. Now, compare it in case of a helium neon laser, what I have written in green there, where the gas pressure is typically 0.5 torr. And when the gas pressure is typically 0.5 torr, you will have tau 0 is equal to 580 nanoseconds. Okay. Actually, there is a formula for when you have the gas pressure, you do have a certain formula from where you can calculate the mean time. Okay. So, that is 580 nanoseconds, that means 10 to the power minus 9 seconds. Delta nu, if you do the calculation, delta nu will turn out to be 0.549 megahertz, and delta lambda will turn out to be 0.0007733 picometer. Okay, so it is delta lambda is 0.000733 picometer, and this is for a helium neon laser where the gas pressure is typically 0.5 torr. Just if I go back one slide, 2 slides, just see the helium, just compare that figure with the helium line, only the helium line, which is 0.1234, 4 zeros and then 18 picometer. Okay. So, that means the natural broadening of the helium line is much smaller than the collisional broadening in a helium neon laser. It is like one order of magnitude more. You have 3 zeros here, you had 4 zeros there, and picometer it remains at picometer. So, it is a comparison. You can take it for many other collisional broadening system. It need not be a laser, it can be anything, and compare it with the natural line width, and you will find that collision broadening is much more. Quite often collisional broadening is called even pressure broadening. As you can see, it depends on the pressure too. Okay. So, pressure broadening or collisional broadening, and the broadening is much more than the natural line width. So, let us go to, we have covered up the homogeneous broadening. Now, let us go to the inhomogeneous broadening. Okay. So, Doppler broadening is of spectral lines, is the inhomogeneous part. Just try to remember, I am sure you would have studied in physics Doppler effect, and in sound, you know, when you are studying sound, quite often it is used in sound. Okay. So, if the source of sound is say here at this point, and the observer is here, and there is one more observer here. If the source is moving in this side, you will get a higher pitched sound or a higher frequency sound will be detected by this observer. And because the source is moving away from this observer, he will get a lower frequency sound. So, this is a lower frequency sound that this man gets, and this is the higher frequency sound which this man gets. So, basically the waves here that are shown in this concentric circles keep getting compressed as the source moves towards this, and as the source moves away, the waves becomes a bit rarefied, it is not compressed. Okay. So, this is what is in sound, and the same thing applies for light or any electromagnetic radiation. You could, you know, in place of a man here or a man here, you could place a detector here, you could place a detector here, and this could be, this is your say an atom or a molecule or any particle that is tumbling down from the higher state to the lower state, and it is giving out some spontaneous emission. So, that electromagnetic wave that is being radiated it is moving. Okay. So, this Doppler effect is because these atoms are moving in that, so movement in that gas, and what you are detecting, the detector is detecting something else other than the actual original frequency that is emitted by the source. Okay. So, now our source is that atom here, which is moving constantly in a gas. Generally, Doppler broadening we associate with the particles in a gas, because that is where these are moving. And when we talk of radiation, it is either called the red shift or the blue shift. That means if the source is moving towards your detector, then you have a frequency which changes to a higher frequency than the actual frequency. So, it is called the blue shift. And if I have a detector here, the detector will record a frequency which is lower than the actual frequency. So, it is called the red shift. So, this detector records a red shift and this detector records a blue shift. So, when I say blue shift and red shift, obviously it does not mean that the whole frequency has become either red or blue. There is the source which has, say, a central frequency omega 0 here. Okay. And if the frequency has shifted on this side, okay, that means the frequency has increased. If the frequency has increased, then it is a blue shift. It is a blue shift with respect to omega 0, not that the lambda has become blue. On this side you have omega 2, okay, which is the red shift. So, I have drawn it on this side. That means the frequency has reduced from the central part. So, that is the red shift. Now we have to, now that you have understood what exactly is Doppler broadening effect, okay, now we must do some mathematical calculations to give a quantitative value to this Doppler broadening or the Doppler shift. Okay. So, if V is the velocity of a velocity component, V is the velocity component along the line of sight to any observer or detector, okay, and omega is the observed frequency and is shifted from the rest frequency. Okay. Here the new term is used called the rest frequency. Rest frequency is when the atom is not moving at all, and omega is the frequency when that atom is moving, and it could be on this side of omega or omega 0, or it could be on this side of omega 0. And c is the speed of light, and v is much less than c, speed of light. Then omega that is detected by the detector is given by omega 0 into 1 plus v by c, okay, 1 plus minus. It can be minus for this detector, it can be plus for this detector, okay, that is what. In a gas at thermal equilibrium of temperature T, the velocity of particles follow the Maxwellian distribution, if you recollect. Okay. So, it is following a Maxwellian distribution, all these particles with a temperature T, and they are moving with velocity c, which is less than the speed of light. Okay. Now, the probability of finding a particle between velocity v and v plus dv is given by the Maxwellian distribution, which has a form of this kind. Okay. Actually, if you take this velocity v to be the total velocity, that means it includes the resultant velocity, which includes the velocity in the x direction, y and z direction. That is why I have put it as v. There should be one more factor here in this formula, which is v square. Okay, the moment I add v square here, this function does not look very symmetric. Okay, I have a v square here and a v square here. Okay, it will, and Maxwellian's distribution is not symmetric. It is not a symmetric function. But here what I have considered is a function I should have written actually Vx, maybe in one direction only. Okay. It is a function just in one direction. So, I have removed this v square here, and this looks like a pretty symmetric function, very symmetric. You can see it looks like a Gaussian function. Okay. It is a Gaussian function. So, this function in terms of velocity pv dv gives you this. Here I have just put down a few formulas which you need to remember. Omega minus omega 0 is delta omega, omega 0 is v by c, and v is given by delta omega by c, dv will become c upon omega 0 d omega. So, all these things I just substitute here and I get something of this kind. Okay. So, this is what my line shape function looks like. Okay. It is a nice little Gaussian distribution. And in a Gaussian distribution, you associate with a mean value here, which is given by mu, which in our case is omega 0. That is the central frequency. And Gaussian distribution is also associated with a sigma, which is the standard deviation, and mu is the mean. Okay. So, this is a Gaussian distribution written in green. You just compare this with this distribution, which we have derived just now for the Doppler broadening effect. Okay. So, it is conventional to give sigma, but then the thing is for a Gaussian, sigma is just this half bit, if you see from the center half, but full width half maximum is this total one. So, from this sigma we should be able to derive full width half maximum. It is not very difficult, it is given as this. You can do some algebra yourself and you will finally come to this conclusion. Okay. So, you see this Doppler broadening increases with temperature and rest frequency and decreases with mass of the emitting particle. That is what you can see from here. Okay. So, this final thing gives you the Doppler broadening. Okay. And Doppler broadening, I will just give you an example, Doppler broadening of carbon dioxide. The mass of the molecule is given here, nu 0 is the central frequency, and 2 into 10 to the power 13 hertz, and delta nu is given by 2.29 into 10 to the power 11 hertz. Okay. So, this is what is Doppler broadening. Okay. So, today we have seen what is Doppler broadening, what is natural broadening, and what is collisional broadening or pressure broadening, and we have made a comparison of all these. And all this is required, for building a laser. That is what I will be describing laser. You must know the line shape function of the medium in which the lasing action is taking place.